Well, hello, I'm going to just go through some of the exercises for Chapter 3, Section 2, and these are questions 6 through to 9. So question 6 is just a simple application of Mobius inversion formula just to obtain a few little funny looking identities here of sums over divisors. And it says use the various ways of doing this, but I'm going to just use Mobius inversion, and in fact we'll see it's just a very straightforward application of Mobius inversion. We'll get these ones out. So for question, just to write down what Mobius inversion is about. So we have f, we've got the sum of the divisors of n, sum f over the divisors of little f, call that capital F. Then we can recover this function little f, so little f of n is the sum over the divisors of n of mu d f of n over d, capital F n over d. So we can apply this, we want to play around with the Tor function, so we just write down what the definition is. So by definition Tor of n is just the sum over the divisors of n1, and we just make 1 the subject, so we just simply apply Mobius inversion, and out comes the formula, and there it is. Very nice, very simple application of Mobius inversion. Similarly, if we're playing with sigma of n, we write down the definition of sigma of n. Here my f of little d is d, and we're going to recover this function here, so f of n is n. Again, it's the sum over the divisors of mu of d times sigma n over d. And that's the formula we have to get. Very easy application. For the third one, to deal with the von Mangold function, we look back to one of the identities in the other video, and that was the sum over the divisors of the von Mangold function is log of n. So we can recover the von Mangold function. Lambda of n is sum over the divisors of mu d log n over d. Now one is tempted here to use log laws and to split this up into 2 bits, so I separate this off. Now I can take that log of n, I can take out of the sum, and then I'd simply have a sum of mu of d over the divisors of n, but we know that sum is 0. And I take the minus on the other side. So we have this desired result that the sum over the divisors of mu of d log d is minus von Mangold of n, since the sum over the divisors of n of mu of d is 0. So 3 very simple direct applications of Mobius inversion. For question 7, some rather funny looking, quite pretty little identities, that if we take the sum over the divisors of sigma of d, that's the same as the sum over the divisors of n over d Tor of d. And the sum over the divisors of n over d sigma of d is the sum over the divisors of d times Tor of d. Many different ways one can do these, prove these identities. I'm going to do it fairly bare hands, and because I want to just mention an important idea that we use when proving these identities, and that is because the each of these functions is multiplicative, this sum over the divisors is going to be multiplicative as well. And this is true for all of these. So to prove two sums are, to prove two multiplicative functions are equal, we only need to check they agree when n is a prime power, and that's what we're going to do. So we're going to prove this result here. So since both sides are multiplicative, we only need to show the result is true when I take n to be a power of a prime. So I'm going to replace the n here with p to the alpha and show we get the same thing both sides. So if n is p to the alpha, we can explicitly write out what this sum is, because we can write down what the factors of p to the alpha are, and I can then evaluate each of these. Now sigma of 1 is 1, but I'm going to write it as p minus 1 on p minus 1 to get the pattern going. And I can put these over a common denominator, and I'll get some powers of p, and I'm going to get alpha plus 1 lots of minus 1. So I'll have a minus alpha plus 1 here. This is a geometric series, so I can sum that one and get this here. The common ratios is p. I've got alpha plus 1 terms, and so I get my sum, and I just copy that one down. Can't really do much more with that, so I'll leave that as it is. Now looking at the other side, if I replace n with p to the alpha, then I get p to the alpha here and p to the alpha here. And again, I can take the p to the alpha out and write out this sum. And I can evaluate the torr value. So torr of 1 is 1, torr of p is 2, torr of p squared is 3, and so on. So we can evaluate this sum. Now this one here, I need to pull in this little, well, perhaps fairly well-known result, but the sum of q times x to the q minus 1 is given by this expression. Now how do you get this? Well, you start off with just taking a sum of x to the q, from q is 1 to n plus 1, and then you can sum that because it's a geometric series, and then you differentiate both sides, and that'll pull the q down the front, decrease it by 1, and I use the quotient rule on the other side. Gets me this expression. Now to apply this to what I've got up here, I'm going to replace x with 1 over p and n with alpha. So I plug all that in, and I get this sum here. Now we need to tidy this up and show it equals the one above, so I'm going to multiply top and bottom by p squared, and that'll be p to the alpha plus 2 will cancel with that one, and so on. We can cancel that through. And you multiply this by p squared, it'll multiply the inside of the bracket by p. You'll get 1 minus p all squared, which is the same as p minus 1 all squared. Keeping your eye on where we're headed towards, I'm going to then split this up into p to the alpha plus 2. I need a minus p, so I've got a minus 2p in here. So I'm going to split that, take one of the minus p's there, and then I write down what I've got left and factorise it, which gives me that. One of these terms cancels. I can take a p out of here, and I get exactly what I had above. So that's equal to this sum here that we had above. And so we've shown the two expressions agree at a prime power, and that means because they're multiplicative, they agree for all n. 7b is done similarly. I won't grind through that, but it's the same sort of calculation that you do. You show each side as the same at a prime power. Question 8 is again another nice little identity here. It's rather cute, this one. It says that you take the sum over the divisors of torr of d all cubed. So you take the cube of these, you get, it's the same as the square of the sum of the divisors of torr d, which is a very rather nice result. And the proof of this one, well, again, we're just going to check what happens at, since both sides are multiplicative, I'm just going to check what happens at prime powers. So I'm going to put n equals p to the alpha in. Start off with the left hand side, so that's this expression here, the sum of the cubes. And again, I'll just write out what the sum looks like, and I can evaluate each of these because we know torr of p is going to be 2, torr of p squared is 3, and so on. So we end up with this one. And we can this now is, it's a well-known result that the sum of the cubes of the integers is just the same as the sum of the integers all squared. This is a result that was known to the ancient Greeks. This sum here turns out to be, well, it'll be alpha squared, alpha plus 1 squared over 4, which is alpha plus 1 over 2 all squared, which is that. So that's a well-known result from elementary number theory, and that of course is just the sum of the squares here. and in fact I realise I've made a slight mistake here. There should be alpha plus 1 cubed, and this one of course will be alpha plus 1 there. So sorry, p to the tor of p to the alpha is alpha plus 1, isn't it? So I get an extra term there, but I also get the same one here for this sum. Okay, so question 9, the last one in this section. This is a problem actually from abstract algebra, nice application of number theory to some abstract algebra. If you haven't done much abstract algebra, you might skip this one, but it's about counting the number of irreducible polynomials in the in Zp of x. So we take p is a fixed prime, n is a positive integer. It is known from algebra that there is an irreducible polynomial in Zp of degree n. And more importantly, it's known from algebra that when you take all the irreducibles, for each divisor d of n, you take all the irreducible polynomials of degree n in Zp of x. Zp of x is a set of all polynomials with coefficients from Zp. So you take the product for each divisor of n, you take all of the monic irreducible polynomials, and you multiply them all together, and you get x to the p to the n minus x. This is an important result from abstract algebra. So I'm going to let n sub d be the number of such irreducible polynomials of degree n. And we're asked to explain this statement here and then find a nice formula for this capital N, the number of irreducible polynomials. So this actually, once we've got Mobius inversion, is very nice. So what we're given here is that x to the p to the n minus x is the product of all of the irreducibles for each divisor of n. So I'm just going to compare the degrees on both sides. The degree of this polynomial is p to the n. And on this side, each irreducible polynomial of degree d will contribute d to the total degree. And there are n sub d of such polynomials. So the total degree will be given by the sum over the divisors of n d times n sub d. And now we can hit this with Mobius inversion, which is a very nice application. So by Mobius inversion, I just get n, capital N of n, is the sum of mu n over d. I'm using that other version of the Mobius inversion. It's normally mu d f of n over d, but you can just sum backwards and write this as mu of n over d p to the d. And then simply dividing by n gives me the nice formula. So there's the formula for the number of irreducibles. So just as an example, if we take p to be 2, so all our coefficients are noughts or ones, and we want the n is 4, so we want the number of irreducibles of degree 4. Well, by hand, you can write out the irreducibles of degree 4 in Z2 of x. X to the 4th plus x plus 1 is irreducible. X to the 4th plus x cubed plus 1 is irreducible. Notice x to the 4th plus x squared plus 1 is not, because that's just, I'll leave you to check, that's just x squared plus x plus 1 all squared. So if you put a square there, it's not irreducible. And finally, this one, we mustn't miss this one. It's x to the 4th plus x cubed plus x squared plus x plus 1. That one also is irreducible. You can't factorise this in Z2 of x. So the number of irreducibles of degree 4 in Z2 of x is 3. And let's compare that with our formula. So we've got 1 over 4, sum of the divisors of 4, mu of 4 over d, 2 to the d. So if d is 1, mu of 4 is 0. If d is 2, mu of 2 is minus 1, and 2 squared is 4. And if d is 4, mu of 1 is 1, and 2 to the 4th is 16. So we get 16 minus 4 is 12 over 4 is indeed 3, which agrees with what we saw by doing it by hand. That's a nice little application of the Mobius inversion formula. So they're the tutorial exercises for this section.